Welcome to Chapter 3. This first lesson is going to be over the atomic theory and how we got to know how the atom was built, and then in subsequent lessons we're going to learn some of the most important math that we need for the year, and so this is going to be an important unit. So let's just dive right in. The first law that we're going to discuss, because there are three laws that basically are the basis of chemistry, the first one is the law of conservation of mass. And the law of conservation of mass states that mass is neither created nor destroyed during an ordinary chemical reaction, okay, or during physical changes as well. And when we talk about ordinary chemical reactions, this does not mean nuclear reactions. They are not ordinary because they are dealing with the nucleus. The second law that we're going to discuss is the law of definite proportions. And of course, if we're talking about laws, you make sure you need to know this for a test because it's actual law. That means, if you remember from Chapter 1, a law means there are no known exceptions. Okay? And the law of definite proportions basically says this, that whenever a compound combines, so let's say I have hydrogen and oxygen combining to form water, they always do so in the same ratio exactly, no matter whether I get that water anywhere on Earth. Same thing, here's another example of table salt, which is sodium chloride. And no matter where that table salt is found, or just the compound sodium chloride, it's always 39.34% by sodium and 60.66% of chlorine, no matter where or how it's formed. The third law is a little bit more difficult to kind of wrap your brain around, but it is called the law of multiple proportions. And the law of multiple proportions basically states that there are some elements that can combine together in different ways. For instance, carbon and oxygen. And when they do so, they're doing so in specific whole number ratios, but that it's not the only way they can go together. For instance, carbon and oxygen can form carbon monoxide and carbon dioxide. And so that's an example of multiple proportion. Some other examples are nitrogen and oxygen. It can form NO into O5, in O2, into O4, just some examples in ways that they go together. Of course, when we get to bonding, that will make more sense. That brings us to atomic theory, and atomic theory is was discovered over a long period of time, but John Dalton was the one we credit or talk about the most, was John Dalton's atomic theory, and so it's called Dalton's atomic theory. Which has 5 postulates, or 5 points of it. And let's get into those. The first one is that all matter is composed of extremely small particles called atoms. Atoms of the same element are exactly the same, he said. And that when by exactly the same we mean in size, mass, all their properties are the same. He also stated that atoms cannot be subdivided, created, or destroyed. And then he said that atoms of different elements combine in simple whole number ratios. And then he said in chemical reactions, atoms are combined, separated, or rearranged. This would be where the law of conservation of mass would be addressed. And then, of course, number 4 would be where the law of definite proportions was addressed. Okay? Put a star by postulates 2 and 3, because we now know that those not to be true overall anymore. And primarily at the time, that's what they thought, but of course since then we've gotten a lot more advanced in our technology and being able to figure out things, and so those two have changed. We still accept Dalton's atomic theory, but the reasons that they have changed are as follows. Number 2 is because we have something called isotopes, which we'll talk about in a few minutes. Isotopes have different number of neutrons, so that gives them different masses. although their properties are still basically the same, they do have different masses, so they're not exactly the same. And then, of course, at the time we didn't know, but we can subdivide atoms because atoms can be, and they can be destroyed in nuclear reactions. But remember, atoms they can be subdivided into protons, neutrons, and electrons. And at the time they didn't realize that. So they can be subdivided. But even though those two postulates have changed, we still accept Dalton's atomic theory, and it was truly groundbreaking at the time. So the structure of the atom, the early models, first of all, we had a Greek philosopher named Democritus around 400 BC. He was the first person to come up with the idea of atom. He called them atomos, which is Greek for indivisible particles. However, his teacher was Aristotle, the famous philosopher, and he disagreed with Democritus. And so since he was the teacher and Democritus was the student, it was almost 2,000 years before his theory was credited. But he is credited with the first person to come up with the idea that all matter had tiny little particles. Okay? J.J. Thomson is very important, and that's because he discovered the electron. And he did so with the cathode ray tube. Okay? So he passed a current through there and he realized that there were charged particles. If you're more interested in that, there's a lot of information to be had on him, but we're just going to hit the highlights. The plum pudding model was used to predict protons because they knew that atoms were electrically neutral, so if it had electrons, it had to have some sort of positive charge. So it predicted protons, although it was called plum pudding because it looked like they drew it kind of like this, and then you just had these tiny little electrons floating around in a sea of protons that were positive. Okay. Then Rutherford came along, and he, who was a student of Thomson, he discovered the nucleus. Whoops. Let me go back. Sorry about that. He discovered the nucleus. And he did this with his famous gold foil experiment, in which he bombarded a thin sheet of gold foil with positive alpha particles or helium nuclei, and he found that there was a small, dense, positive region. What he expected was for all of the alpha particles to pass straight through, but what actually happened is some were deflected, and they were deflected in a very energetic way, so he concluded that there was a small, positive region that contains most of the mass but takes up very little space. So from that we came up with the atom, and that's the smallest particle of an element that retains the chemical properties. Okay, so if you have just the protons, just the electrons, just the neutrons by themselves, they do not retain those chemical properties. Okay, the atom, of course, you know this from junior high science or maybe even earlier, contains two regions. We have the nucleus, and of course surrounding the nucleus is the electron cloud. So when we have the parts of the atom, let's talk about the protons. Of course, the protons are positively charged and they are located in the nucleus. Okay? The number of protons cannot change for an element in an ordinary chemical reaction, so they're always going to be the same. Therefore, we identify our elements by their number of protons because they won't change. The symbol is a P plus because it's a positive. Of course, the charge is a +1. And the mass is 1.637 times 10 to the negative 24 grams. Okay? This is approximately 1,837 times greater than the mass of an electron. So they're much more massive than an electron. The neutron is high energy, but it's neutrally charged, and it is also located in the nucleus. Okay, the neutrons can change for an element, and neutrons stabilize the nucleus by using nuclear forces, which kind of makes sense, right? Nuclear forces stabilize the the nucleus. The symbol for those is N0. It has a 0 charge because it's neutral, and the mass is 1.675 times 10 to the 24 grams. Okay, they are approximately the same as the proton. So that's the main thing you need to know about the masses of protons and neutrons, is that they're roughly the same and that they're much, much heavier than the electrons. The electrons, of course, are the negatively charged, and they are located in the electron cloud. And they're spinning around very, very fast, which we'll talk about that in Chapter 4. The symbol is E negative because it's got a -1 charge, and its mass is 9.11 times 10 to the 28th grams. And of course we said that was 1/1837 of a proton. So much, much lighter. Okay? When we're talking about the two parts of the atom, the nucleus contains most of the mass, but the electron cloud contains most of the volume. Okay? So remember, the electron spinning around very, very fast, but it's taking up most of the volume, but the nucleus is small and densely packed, and that's where most of the mass comes from. This is small and densely packed, and atom is mostly empty space. So that brings us to isotopes, okay? Remember we said that the postulate of Dalton's atomic theory that atoms have the same or exactly the same. Well, we found out with improved balances and techniques that they are not the same in mass always, because they have something called isotopes, which have different amounts of neutrons. So it's atoms with the same number of protons, because remember we said those don't change, but they have a different number of neutrons. And because of that, it gives them a different mass. Okay. Usually the isotopes are referred to by their name or their symbol and then their mass number. Every element on the periodic table has at least two isotopes. There's nothing that only has one. Everything has at least 2 isotopes. Some elements can have as many as 25 isotopes. Okay. So remember, isotopes have the same chemical properties but different masses. Okay. So when we are writing the isotopes, we can write them in a number of different ways. Sometimes when you see the symbol like this, we're going to do this and draw this in your little box, and we can draw it like this, 23 and 11. And we refer to this as A and this as Z. Okay? And Z is your atomic number, which is how we identify elements. So in this case, sodium is going to be identified by 11, and then the mass number is going to be your protons plus your neutrons, okay? And that's always on the top, okay? So the nuclide is what a general term for any isotope or element. So we might say a nuclide of sodium, meaning we are referring to a specific isotope of sodium, not just sodium in general, okay? The other way that we can write this in the other box that you have is sodium 23, which, so in that little box underneath that, we could also refer to this as sodium 23, which means that I have a mass number of 23, okay? The atomic number Z is your number of protons. And that identifies the element, not by electrons. We identify it by protons. Because the atoms are neutral, they contain the same number of electrons as they do protons. But we don't always deal with neutral atoms, okay? So you have to remember that, okay? The mass number is your protons plus your neutrons. Okay? So if we have our mass number, we can identify how many protons, electrons, and neutrons are available to us in that particular isotope, okay? Hydrogen is a special case, okay? And it's such a special case that they give each isotope of hydrogen its own special name, okay? So they all have 1 proton, because remember we said that doesn't change, okay? Protium, which is the most common form, has 0 neutrons. It's the only element that has 0 neutrons. Deuterium has 1, and tritium has 2. They all have the same number of electrons, okay? This one is the most common, proterium. But deuterium is also fairly common. We sometimes refer to that as heavy hydrogen. Or sometimes if you have water made with deuterium, they'll call it heavy water. And that's because it is slightly heavier with that one extra neutron. Okay? So let's just see how, because this is what your homework's going to be on, let's see how we identify number of protons, neutrons, and electrons. Okay? So we're going to practice with these three. So I have uranium-235, and so we're going to do protons, neutrons, and electrons. Okay? So I look at my periodic table, and I see that the uranium has an atomic mass of 92. So it's got 92 atomic mass, not atomic mass, excuse me, atomic number. So I look on that, and so I would say it has 92 protons. Because this is a neutral atom, it would have 92 electrons. And then in order to get my number of neutrons, I'm going to take 235, because that's my mass number, and I'm going to subtract 92. And when I do that, I will get my number of neutrons, which would be 143. Okay? Now let's do this with carbon-14. If I look at the periodic table, I see that the atomic number, which of course is equal to my protons, for carbon is 6. So that means that it's going to have 6 protons and 6 electrons. So now I would take 14 minus 6, and I would get 8. So it would have 8 protons. Neutrons, excuse me, neutrons. Potassium, 39, has an atomic number of 19. Remember, this is atomic number up here, and we got that from the periodic table. Okay? So it's 19 protons, 19 electrons, and then in order to get my number of neutrons, I'm going to take 39 minus 19, which is 20. So it would have 20 neutrons. Sodium-23 has an atomic number of 11. So that means I have 11 protons and 11 electrons. So then I would take 23 minus 11, and I would get 12 neutrons. And so that's how you're going to do that. Okay? There's something that you can use called APEman to help you remember that if you need, and that is atomic number is equal to protons and electrons, mass number minus atomic number equals neutrons. Okay? The other thing is when we wrote that symbol like this a while ago, we said sodium 23, 11. It's kind of nice because it actually sets up a little subtraction problem for us right there, and that would be our number of neutrons. So you can do it that way as well. Okay? On your worksheet, though, a couple of things show up like positive or negative isotopes. So I want to show you that real quick. Okay? So let's say you have a symbol that looked like this, Na plus, and they said it was, they said 23 right here. Okay? So you know, we looked up a while ago that the atomic number is 11. Okay? So if we do the protons, neutrons, and electrons, I still have 11 for protons because that doesn't change. I subtract and I get 12, but because of this positive sign right there, it's telling you that it lost an electron because it's positive. So now this would actually be 10. Okay? Let's do another one. Let's say I had sulfur, and it said 2 minus, and it said that I had sulfur, let's say 34. Okay? I look up the atomic number of sulfur, and I see that it's 16. Okay? So protons, neutrons, and electrons. Protons are going to be 16. 34 minus 16, of course, is going to give us our number of neutrons, which would be 18 neutrons. But then, because this is a negative 2, remember electrons are negative, so that implies that it gained 2 electrons. Because remember, we're adding or subtracting things that are negative. So instead of 16 electrons, like the atomic number says, it would have 18. And that's because it has a negative 2. Because now it has 2 extra electrons than it should. Okay? That is where we're going to stop this lesson. and I will see you in class.